In this video, we're going to look at an example of using a differential in an application problem to figure out an approximation. So we've got a closed cylindrical can. We're going to make it out of metal. The can is to be 10 centimeters high and 4 centimeters in diameter. The top and bottom need to be 1/10 of a centimeter thick, and the side needs to be 5/100ths of a centimeter thick. And we're going to use differentials to estimate the amount of metal. So the idea here is that this cylindrical can holds a certain amount of volume, and then the metal also has a little bit of extra volume. So if we think about changing from the inside, whatever the can holds, to just a little bit of a change to represent the metal, if we can estimate that change in volume, then that change in volume literally is the amount of metal that we're looking for. So first we'll start with the volume formula, which is pi r squared h for a cylinder. And we're going to find the differential of the volume. So when we find the differential of the dV, we'll do the partial with respect to r times dr. Well, derivative of r squared is 2r, and pi and h are just constants, so our partial derivative in that case is 2 pi rh. So the first part of our differential becomes 2 pi rh dr. When we differentiate with respect to h, pi and r squared are constants. Derivative of h is just 1, so that second part becomes pi r squared dh. Again, if we think about the thickness of the sides and the thickness of the top and bottom as change in the radius and change in the height, then we can estimate the amount of volume of the metal, which is going to be the change in the volume, by looking at these little changes in the radius and the height, and where we started with the amount of what the original radius and height were. All right, so the original radius is 2, since they gave us the diameter, so we'll use r equals 2. H will be 10, that was the original height. The sides are 5/100ths of a centimeter thick, but that sides is going all the way around, so our dr is just 0.05. However, for dh, I've got 1/10 of a centimeter thick on top and 1/10 of a centimeter thick on bottom, so my dh is actually 0.2 by the time I add the top and bottom on there. So our differential of v evaluated at these points will be 2 pi times 2 times 10 times 0.05 plus pi times times 2 squared, which will be 4, times 0.2. If you put that in a calculator and get a decimal approximation, you should get about 8.796. So we conclude that the amount of the metal in the can is approximately 8.796 cubic centimeters.